David Johnson from Mark Astrophysics is here, and he will talk about the test of interferometry with the EC of the test of the equivalence principle. So, I'll flash 5 minutes.
Okay. Well, great. Thanks. Thank you for the opportunity. I'm here because Mark unfortunately couldn't make it, but I'll be discussing some ideas we have and progress that we're currently making on really long baseline atom interferometry. So atom interferometers have now been around for almost 20 years, and we're investigating the question of basically we can take this really great tool, and if we increase the baseline, increase the interrogation time, we should be able to dramatically increase the scaling, the sensitivity scaling is linear in length, so that's favorable at least to increase the size by, say, a factor of 10. So the first experiment that we're proposing, that we're actively building right now with this tool, is a test of the equivalence principle. So why test the equivalence principle? So there's, this is really a good starting point to work out the systematics for such a really large-scale device. And also, in its own right, the equivalence principle, since it's one of the fundamental axioms of general relativity, and it's testable, it's really a great experiment to do, and it has a long history, so it's been tested since Galileo. And the current limit is now a part in 10 to the 13, so that's delta A over A for the variation between two different composition test masses and their average acceleration. So the other neat thing about this is it's set by two very different experiments. One sort of large scale, so this is lunar laser ranging, really looking at basically the distance between the Earth-Moon system as they both fall towards the sun. And so that's a laser in Houston reflecting off of a reflector set by the astronauts on the surface of the moon, and looking at time of flight of photons. And then the ETWASH group in the University of Washington is looking at basically torsion pendula of beryllium and titanium, and again measuring the exact same limit. So they're both at a part in 10 to the 13. So what can we learn about sort of fundamental physics using tests of the equivalence principle? So these tests are very effective at constraining fifth force theories and scalar fields. So this is a alpha lambda plot, which is basically parametrizing changes to Newtonian gravity using a Yukawa potential. And so here we basically are starting at a meter going to 10 to the 10 meters, and then alpha ranging to, so we're in the large lambda, small alpha regime, as opposed to the stuff that, that Alex Cronin was talking about in the really small lambda, large alpha. So these solid lines here are basically new potential theories of sort of new physics. So this is a fifth force. The B stands for coupling to baryon number. B minus L is coupling to baryon minus lepton number. And the dilaton is for a scalar theory. So the solid yellow here is the current constraints by experiments. And then the dashed line is what we are projected to be able to achieve with our sensitivity. Okay, so a brief introduction on the experimental technique. So everything I'm going to be talking about is light pulse atom interferometry. So we have a scenario where we have a vertical atomic fountain, and the atom is freely falling, inertial in this system, and we can treat it as a two-level system, or it can drive Rabi oscillations between the two levels. And so then we have a convenient method to be able to make beam splitters and mirrors to build a time-space interferometer where we separate, due to momentum conservation, we separate the two arms of the interferometer, so between a state that absorbed a photon and a state that didn't. And then we apply a mirror pulse here, and then a final readout pulse to look at the interference. So the time here, the interrogation time, sets the sensitivity, and this separation here is a function of basically how much momentum you transfer to the atom. So what is the signal, the output signal of this device? So the total phase shift here can be broken down into 3 different components. So propagation phase shift, laser phase shift, and separation phase shift. So we had some good discussion from the neutron interferometer talks about propagation phase shift. So the way I'll talk about this here is going along these 2 different paths, the atom has a different Hamiltonian during its free space evolution, and so it really evolves phase at different rates along the upper and the lower path. So this is analogous to if you put a phase shifter in one arm of the neutron interferometer, you're going to apply a different phase to that arm. So if you have a different potential along those 2 paths, you see a different phase shift. So again, these scalar on-off Bohm effects and things like that. So then at the end of the interferometer, you have effects that if you don't have perfect overlap between the 2 wave functions, you're going to get a phase shift due to wave packet separation. So both of these are certainly measurable effects, but they are completely dominated by the laser field interaction. So from a simple point of view, really what we're doing is marbles and rulers. We just have a very good ruler with the laser field and a very nice test mass in the atom. So every time the laser interacts with the atom, it imprints the laser phase onto the atom, and that goes like k dot z. So we get laser phase from each of these 4 interaction points, and we see the total, the sum total of basically the distance traveled there. So the dominant form of the phase shift looks like k of the light times gt squared, which in our vertical geometry is the distance traveled. So now, just to give you a sense, this is actually a really good measurement of phase. So we can get phase shifts that have been demonstrated of 10 to the 6, 10 to the 7 radians, and in our new generation, pushing towards 10 to the 8, 10 to the 9 radians. So even making a measurement where you determine the phase shift to a single radian is already a really good precision measurement, let alone splitting a fringe to a part in 10 to the 6. Okay, so this is the most recent work done by Mark in terms of building one of these atom interferometers. So this is a setup of actually 2 atom interferometers set up as a gravity gradiometer. So they're separated by 1 meter, and we're sensitive to, so K effective here is horizontal for both of them. So you can see the wave packet separation between the 2, and so it's sensitive to horizontal accelerations. So this has, the purpose of this experiment was for precision navigation and geodesy. Basically, it was designed to be mobile, so you could drive it around and do gravity maps. It also turned out to be interesting just for some sort of neat fundamental physics stuff. So this is another version of an experiment where Mark measured the gravitational constant, which was done in a similar manner with a vertical version of this. Here we have several hundred kilograms of lead, and they're on stepper motors, so they're moved in and out, chopping the phase shift, and you can see, you know, a beautiful 1/10 of a radian phase shift basically by separating the lead by 2 meters and bringing it back together. Now the neat thing, so this is the sensitivity, demonstrated sensitivity for one of the interferometers. So this is an Allen deviation plot, and we're integrated out for 10 to the 5 seconds here, and it's a few 10 to the minus 5 radians. So this gives a demonstrated accelerometer resolution of 10 to the minus 11 little g, which is fantastic sensitivity, and that's for an interferometer with an interrogation region that's 10 centimeters. So now the obvious thing to do is to say, well, if it works well at 10 centimeters, why don't we go larger? So scale it up by a factor of 100. And so that's what we're doing. So this is not portable. So this is a 10-meter tall drop tower in the basement of the Variant Physics building at Stanford, where we're looking now, instead of millisecond drop times, we're looking at 1.3 seconds is the drop time. And so with a K effective, so 2 h bar k atom optics, so basically every time we interact with the atom, it scatters 2 photons. So we get 3 times 10 to the 8 radians sort of per shot. And then if we integrate for a month of data at 10 to the 7 atoms per shot, we believe we can basically have a sensitivity of 10 to the minus 15 little g. So that is a really exciting number because, first off, it's 2 orders of magnitude better than the current limits on the equivalence principle, and it really opens the door to a lot of new physics in terms of what can we really test when we have an acceleration sensitivity that's that small. So then, of course, there are some exciting possibilities for improvement. That's for 2 photons. There are some ideas out there. This has been demonstrated in meter scale apparatus with 20 photons. And we believe we can push it to 100 photons. So that, again, scales linearly with K effective. So you can really push the sensitivity dramatically, and that reduces your averaging time, which would be phenomenal in terms of 1 month of averaging is the number we put in because basically that's the longest that we think we can get anyone to believe that the experiment will be stable. I showed you before 10 to the 5, or sorry, averaging for 10 to the 5 seconds, and this is 10 to the 6 seconds.
So bottom line, what is the ultimate sensitivity that you can imagine pushing this in the future compared to other experiments?
So what we put down at for far future is 10 to the minus 19. So that's that's speculative. Well, so the 2 advances that requires are these large momentum transfer beam splitters and also Heisenberg statistics, so squeezing from the talk that we heard previously. So as you can see.
No, I want to make it clear because you're competing with experiments like ESA, various step kind of experiments. So you're actually beating their claimed sensitivity. Is that correct?
So they're
and you're both at Stanford, so you talk about this, right?
Yeah, well, I think STEP is claiming 10 to the minus 18 for their satellite.
Right, you're claiming 10 to the minus 19.
Well, I say 10 to the minus 19 like 30 years in the future. They're only a few years in the future. That's, I mean, 10 to the minus 19. That is a published number, but again, I say that's far future. I'll stick with 10 to the minus 15 for certainly for my graduate school career. Okay, so what is the experiment that we're proposing to do to test the equivalence principle? So we're going to use co-falling rubidium-85 and rubidium-87 as our 2 different test masses. So they differ by 2 neutrons. It's 2% roughly mass difference. That will evaporatively cool to less than 1 microkelvin, but not to Bose-Einstein condensate. So basically, for all the reasons that we heard in the last talk, we really do not want to have an interacting sample. So it's really important that we're basically doing the experiment, a single atom at a time, just a million at once. So we don't have interactions to deal with. And again, so basically the reason why we need to go so cold is our main systematics arise from kinematic differences between the 2 isotopes. So we need to be able to define our velocities and our relative velocities between the 2 samples on the order of the micron per second level. So that means we need millimeter per second velocities with 1 million atoms. So with square root n statistics, we now have a defined center of mass behavior that's down to a micron per second. So then again, so what I said before, 10 to the minus 15 with 1 month of data collection. And now what I'm going to strive to convince you of is that we understand the systematics so that 10 to the minus 15 is a reasonable number. Because sensitivity is one thing, but the systematic uncertainty is really quite another. Okay, so this was with shot noise limit, atom shot noise limited detection. So what about technical noise? seismic vibration, laser phase noise. So these are two really serious problems. The seismic vibration is something like 10 to the minus 7 little g, 10 to the minus 8 at the base of our pit. So to try and make an absolute measurement to 10 to the minus 15 is pretty much crazy. The best absolute atom interferometer gravity measurement is the 10 to the minus 10 work from Ock and Peters. And again, they were worrying about all sorts of things like water table fluctuations, you know, where the moon is, and so on and so forth. So we're going to rely on common mode suppression here. So if we run the interferometer simultaneously for both isotopes, then using the same laser, so basically we use the same K effective to talk to both isotopes, and G then for both isotopes is the same because we'll do our best to make them follow the same trajectory, the same spatial location at the same time, then any fluctuations that we see or that certainly exist on the environment will be common to both species. So why do it with the two isotopes of rubidium? That's basically completely driven by this laser phase noise question. If we wanted to do rubidium cesium or cesium lithium or something like that, we'd need a frequency comb to control K effective between the two isotopes to a part in 10 to the 15. So that's a question. Now, possible is really quite difficult. So much easier just to use the same laser, and then the requirements on laser phase noise are drastically reduced. Okay, so you're not meant to be able to read any of this. So this is a list of basically all the phase shifts that that we've calculated that affect the system, and you know they go down to part 10 to the minus 16 from fractional size of 1. So where do they come from? We're doing this on the Earth, so it's a rotating platform, and the atoms are coupled to the Earth through the retroreflecting mirror. We have gravity anomalies and gradients. So again, this is really a kinematic question. If the two isotopes really follow the same trajectory, then they will see the same gravity up to gradients, and that's not a problem. But we won't be able to make the two isotopes follow the same trajectory, purely because, I mean, they just have different masses. So if we transfer the same momentum to them, they will end up with different velocities, and they'll explore different spatial locations in the system. Again, as was nicely mentioned earlier, it's rubidium, so we can put them in the same magnetic field insensitive state that Jerry Schwinbauer was talking about. So then they're only sensitive to second-order Zeeman splitting. So our sensitivity is reduced, but they just have different second-order Zeeman coefficients. So we're sensitive to basically gradients in the magnetic field. So we need to control our magnetic field gradient to then 10 nanotesla per meter, which isn't quite as bad as it sounds. That's been demonstrated before. Again, people have been really worried about this for a long time. So proof mass overlap. If you start them in different spots, so if we're going to load both isotopes into the same magnetic trap, but then because they have different masses, they have different amounts of sag in the magnetic trap. So a good number to carry around with you is that the gravitational gradient, basically just because we're outside of a spherical Earth, is 10 to the minus 16 G per nanometer. Those are useful units. So what that says is that we need to control to know the relative starting offset to 10 nanometers in our trap. So that's basically our most stringent. So the difference happens to be 100 nanometers. So control it to 100, know it to 10. Okay, and then there's all sorts of misalignments, finite pulse effects, etc. So I claim that we appear to be able to control this at the 10 to the minus 15 level, and the main one that I'll talk you through is rotations, and then there's a paper in the proceedings of the Enrico Fermi School of Physics in Verona where we go through basically in great detail every single one of these effects. Okay, so this is the system, so it exists. This is it getting lowered into the basement, and this is what our interferometer region looks like. So you can see our 3-layer mu metal magnetic shield around the vacuum tube that we're using to control magnetic fields. And so this is we're basically, our progress right now is we're very close to installing our atom source at the base of the pit to start doing 10-meter interferometers.
So when I'm looking down on there, I'm looking down 10 meters down to the floor.
Yep, yep. So the pit itself is 25 feet deep and it's 8 feet around.
Yes.
And then the height of this aluminum structure is 10 meters.
And the only way to get down to the bottom is to go down that ladder?
Yep. So this pit was actually from GPB. They were doing, they wanted a very vibrationally quiet environment. So they did their initial gyroscope testing down there. So the floor at the base there is an order of magnitude better than it is up here in terms of seismic isolation. Okay, so our system in terms of the atomic physics is a conventional sort of 2D MOT loading a 3D MOT, where we don't have, we're not trying to make, to do anything really all that much better than anyone's already done before. So, you know, start with 1 billion atoms and evaporatively cool down to 10 to the 6, 10 to the 7. This is the system, and it does make cold clouds. So we're in the process of evaporatively cooling. That's basically the status of the experiment. Okay, so now some quick discussion of why 10 to the minus 15 really is hard to do, but why we think we can achieve it. So we have this leading systematic, which is due to Coriolis. And this comes about that while the atom's in free fall, it's the vacuum chamber is really rotating because it's fixed to the Earth. So that means our interrogation lasers are also rotating. So every time we flash on a pulse of light, they've now moved, and so that couples Coriolis force into the system. So the systematic looks like basically K effective times the differential velocity. So this is a differential systematic times the rotation rate of the Earth. So basically, for what I said earlier, because we only have we have 1 million atoms and they're cooled down to 1 millimeter per second, we can only really control the differential velocity. It doesn't even really make sense to talk about it below a micron per second. So we're stuck with a micron per second here, and we're stuck with 10 to the minus 5 radians per second, between 10 to the minus 5 and 10 to the minus 4 radians per second of Earth rate. So that means this is, the fractional size of this is 10 to the minus 11, which is 5 orders of magnitude above our limit. So how can we fix this? Well, we can rotate our retro mirror against the rotation rate of the Earth and do it to a part in 10 to the 5, which is about a nanoradian per second, which reduces the fractional error to a part in 10 to the 16. So this is difficult. Good experimentalists will see basically that we're asking for about the limit of what you can do with any system. A good rule of thumb, you sit there, if I want to try and do better than a part in 10 to the 5, that's going to be really hard. But at a part in 10 to the 5 measurement, it's feasible. So turns out you can go out and purchase piezo actuators that have incredible noise floor. So this is 2.7 picometers peak-to-peak noise. And this is a system of 3 piezo actuators with a very thick thermally stable mirror inside a vacuum chamber. And so then what we can do is we can tilt this mirror precisely with Earth rate, and the idea is to be able to reduce our...
What is it that you plotted there?
Oh, so this is just a reference input signal, so basically 6.5 hertz. This is from the company that manufactured the actuators. So they're showing that if they take a spectrum then of looking at basically a resistor, which is telling them the position of the
Linear displacement. So what about though when you put it like, then you have rotational noise too?
Yeah.
Rotational noise, right?
Right. So we're extrapolating our well, we're ultimately going to measure it, but yeah, the rotational noise comes from the fact that we have 3 of them. We have to move all 3 of them. Yes. So this is we've built it, we haven't tested it. So this is the claim is that this is merely a tantalizing plot to say we're not completely crazy, and the next time I give this talk, I'll have data.
Noise you've seen.
No, this is not rotational noise. This is actually only you know, we've repeated this data from them and see actually just a slightly higher noise floor than what they have. But at least for the linear displacement, it is pretty much as advertised. Okay, so that's the state of that experiment. So now I want to take the rest of my time and discuss these basically 3 new experiments that are the next generation after the equivalence principle that really open some new doors to potentially some really interesting laboratory-based physics for studying gravity. So with 10 to the minus 15 sensitivity, are we directly sensitive to general relativity inside the laboratory? I mean, basically all tests of general relativity to this date have been with massive objects far away, looking at the precession of Mercury and so on, or GPB in orbit. Can we do this in a laboratory-based experiment with controllable, tunable experimental parameters? So we take a PPN metric. So here, the gamma and beta terms are 1 in regular GR. So this is just a way that people tend to parameterize when they're discussing basically limits put on deviations from general relativity. And the terms that we're sensitive to, so basically just to give a flavor, so we have Newton's gravity here looking like grad phi. There's a term, a nonlinearity in gravity that basically that gravity gravitates. That goes like grad phi squared. And then also the kinetic energy of the atom gravitates. So these are both tiny effects. So phi g is like 10 to the minus 9 g. And we're sensitive to changes on the interferometer scale. So we get to look over 10 meters over the radius of the Earth. So that puts an effect at 10 to the minus 15 little g from gravity itself gravitating. And again, this v squared g, because we're going slowly, so these are slow particles inside weak fields, but still is a term that's on the border, on just the edge of our sensitivity. Okay. So again, these basically another thing to, okay, that's what I'll say about that. So why do we think we're able to measure them? So this is another phase shift list like what I showed before. And so the important things to look at are the 6th term and the 8th term here. So they both scale, so they scale with v launch. So the velocity, the launch velocity of the apparatus. So what that means is that we have a parameter that we can tune. So by adjusting the launch velocity, the effect changes. So that means we have a chance at actually picking it out among the background, so that if we scale v launch, we can then look to see if we can pick these terms out. Now, that's in any sort of experiment like this, it's always difficult to do just because you're looking for a small signal on top of a really large background. But at least it's a handle that we can tune to. So this, again, to answer your earlier question here, this is what we talk about initial, upgrade, future, and far future. So far future is the 10 to the minus 19. So the initial, we talk about looking at these PPN parameters at, 10 to the minus 1 or something. So, and then this is not, I should stress, is not quantum gravity. This is purely looking at just at general relativity affecting essentially these classical atoms using an atom interferometer. Okay, so the next sort of tantalizing experiment that we can consider is looking at a scalar Aronoff-Bohm effect by, again, so this comes in the propagation phase. If we separate, so these large momentum transfer beam splitters offer really the tantalizing opportunity to put really large differences between the 2 wave packets. So this is actually the physical separation between the 2 wave packets with 2 h-bar k atom optics with a 10-meter interferometer. But scaling that to 100 h-bar k, we can imagine getting separations that really are on the meter scale. So this is interesting from sort of fundamental science from dephasing questions. So we had this discussion over is there a fundamental limit basically to the looking at, if we look at this large distance, there are some theories that talk about that we should expect dephasing of the wave packets, that we really just won't even see contrast as we scale up our size. But then it also gives us the opportunity to put really large scale things here and imagine putting 10 or 100 kilovolts along two electrodes and then seeing a difference to that voltage. And this, because of basically our fantastic sensitivity, we can potentially do a 6th order of magnitude increase on the charge per nucleon. So this is how it's usually written, as number of nucleons and charge per nucleon with the charge of the electron and then the voltage that we see there. Okay.
I didn't get the around foam type part of that. Let's see.
Oh, so this is to the scalar on-off foam. So really just putting a potential
switched on
while they're in there. Yeah, that's key. So gradients, if they're on all the time.
Supposing the rubidium atom has some charge.
Yes, exactly.
Right.
Yeah. So this,
but not deliberately putting some charge.
But not deliberately charging them. No. Right now it's known basically that atom charge neutrality is good to a part in that they really, the atom or the proton and the electron, really share the same charge down to 10 to the minus 22.
Right, I got it.
Yes.
And the polarizability of the atoms, how that?
Yeah, so that's a scaling basically in the sensitivity of this. So crazy ideas are to use really polarizable molecules to even to further increase the sensitivity. Yeah. Okay, so then the sort of the most controversial part of this.
Oh, no.
No, maybe I shouldn't say that, actually. What we're proposing to do is really no different. I mean, the important thing here is to realize that this is no different than LIGO. We're not actually trying to say anything different than LIGO. The only difference, we're basically proposing to do LIGO, but drop the mirrors. So, and atoms are you can get as many as you want, so they're easily replaceable, as opposed to LIGO's mirrors. So this allows us to decouple ourselves from seismic noise and vibrations very handily. So we really are able to get away from basically what limits LIGO's sensitivity due to basically the fact that they're directly inertially coupled. I mean, they do an incredible job at isolating themselves from the environment, but it's a very, very hard thing to do. So this is the usual thing that we're proposing something that's looking in the 0.01 to 10 hertz frequency band, where there are a lot of interesting sources. And the picture to keep in mind is that if we have if we have two objects separated and there's a strain, a delta L over L of an incoming gravity wave at some frequency omega, the distance between the two objects is going to modulate like the strain times sine omega t. Okay, so again, this is the metric that we put in to the calculation, and this is sort of a good intuitive way to see where this comes from. So the position modulates with this strain. So with two derivatives, we see this omega squared, HL omega squared, sine omega t behavior. So then the phase shift, we're sensitive to accelerations, Ka t squared. So the real hand-wavy quick estimate is that we should see something like K HL omega squared sine omega t times basically how long we look at it. So doing the full relativistic calculation, you can see the answer in the limit of these as small quantities basically comes out to the same answer. So that's the flavor for what we're doing. So the proposed experiment, so let's see, I'm going to run out of time. I've basically said this already. The test mass is inertially, it's decoupled, it's freely falling, insensitive to vibration. We're just replacing the mirrors with atoms, and the laser is phase noise. So the laser vibration and intrinsic phase noise are really the limiters to this scheme. Okay, so this is the proposal. We're running two widely separated interferometers. So we build an accelerometer here and an accelerometer here, and we use a common laser to span the two and look for differences in acceleration between the two accelerometers. So by looking at the difference between the two, we really decouple ourselves from basically we can beat down phase noise that way. The inherent vibration, noisy seismic vibration is significantly reduced, and it also, with a really long baseline, so notice 1 kilometer here, so this is planned, we're talking about putting this into an old mine shaft or something like that. We can then also have long drop times, so 10-meter drop times, which are free falls of about 1 second, so then we'd be maximally sensitive in this really interesting frequency range of about a hertz. So the key to take away from that is that really we're looking at the differential phase shift from 2 spaced accelerometers. So what really limits this is that you can't shield gravity gradients, and seismic fluctuations, surface waves, and things like that really are just the moving around of external mass gives you gradients that will affect your signal. And the point of this plot is 0.3 hertz. So you can see 0.3 hertz right here is just a corner frequency. And that's basically, when we talk about our sensitivity, that's the limit. So this is the sensitivity plot. So this is strain per root hertz here, and this is frequency. So this is LIGO's classic curve. And this is one kilometer, the red line here, is 1 kilometer in 0.1 hertz to 1 hertz regime, and then this is 4 kilometers. So it's not, it certainly doesn't have quite the reach of LIGO sensitivity, and this 1 kilometer apparatus doesn't have LISA's sensitivity, but it's an interesting sort of alternative frequency band, and it's really important to try and measure all of these frequency bands. And for large sources fairly close that are really believed to be out there, it's potentially sensitive. All right, so basically these are just the recap. Equivalence principle is the first thing we're going to do to really convince ourselves that we understand the systematics and the performance of such a really sensitive device. Then looking for GR in the lab, atom charge neutrality, and potentially gravity wave detection. So there's lots of people working on this. All the theory comes from Savas's, Dimopoulos' group with Peter Graham and Mina, and then my fellow graduate students and postdoc, and then my professor. Thank you very much.
I'm a little confused about the GR tests in the lab part.
Yes, okay.
Because you emphasized that the basic way that you get rid of noise is by looking at differentials between the 2 types of atoms, for instance. I don't think anybody expects that the self-gravitation, the gravitation of the Earth's gravitational field is going to depend on what what atom you're using. So don't you?
Oh no, for sure. So it's not the running a test. So using the same scheme with 2 different isotopes won't help us at all. Yeah. So it's really.
How do you get your noise down?
It's this scaling with V-launch. So the fact that we have this scale parameter, so we can really look at differentials with. So we can run 2 interferometers with different V-launches at the same time, and then look at differences between those and correlate using using that as an independent parameter rather than the isotope.
What's the status of the big G measurements, and in particular, what about eddy currents in the source mass?
Oh, okay. So the big G measurements, that was so that apparatus has been basically taken apart. So it's the most recent status. I believe Tino's group in Italy has the best limit on that now. I think a factor 2 better than what Mark's work at Yale did. But basically, I think you're exactly right that the source mass characterization is really the limiting systematic at that point. So really understanding the behavior of the source mass electrically and.
So is a new big G measurement likely to be accomplished by your group?
No, we're not planning on doing that.
How hard is it to do experiments with other elements like cesium or lithium or whatever? I mean, are you limited to doing that? Or if we found some other element that was of interest for some other reason, could you do an experiment with?
Yeah, so there's a few sort of technical details, some minor and some not so minor. Lithium's a pain to work with. It's really hard to cool. But Mark has a lithium BEC apparatus, and so that certainly does work. The lasers aren't as good for lithium, but again, these are sort of technical details with enough fortitude you can get around. Cesium works just fine. With this experiment was originally conceived as maybe a differential between potassium and rubidium or rubidium-cesium. Again, we decided to do the 2 isotopes of rubidium purely for the systematic getting rid of the technical noise due to laser phase noise.
But I'm thinking of 2 isotopes of some other element.
Yeah, so you could do
broader range than just rubidium.
So you could do 6 and 7 lithium, and so on. For sure, it's just since rubidium's easy. It's the it's the easiest one, so we're going for the low-hanging fruit.
First have to cool them. So
Yep. Yeah. So yeah.
You had 2 detectors that were separated by a certain distance and that would help get rid of seismic noise, right? You said, can you turn around? I presume it's maybe then also the most sensitive seismic noise detector, right? Is that maybe useful? Are you guys exploring that too?
Well,
Too sensitive.
not in this slide deck. Sorry. Mark's company, AOSense, has actually data from looking at an offshore earthquake in Honduras, and you can completely see the seismic. I mean, they work as seismometers. Totally. A good tidbit is that so to give you an idea how sensitive these are. So this continent used to be covered in glaciers, and they melted. So the glaciers depressed the continent, and the continent is now rebounding so it's called post-glacial rebound, and so that's part in 10⁻⁹. So we're looking for 1,000,000 times better than that.
Do you get trouble from graduate students walking by the apparatus?
Oh yeah. No, my mass is certainly a very sizable gravity gradient. So absolutely.
Sure you're losing weight?
Yeah, exactly.
First, this
More questions for Dave?
Thank you.